In this section, we're going to look at a special type of relationship between variables that is called a function relationship. Within mathematics and algebra in general, we see lots of different relationships between variables, and we try to visualize these relationships a lot of times using graphs. A function relationship follows certain rules that other relationships may not follow. So it's a very specific relationship that we're looking at. So the sort of definition that we have for functions is our first thing here, where a function is a special type of relationship between variables where each input x, we think of x, the independent variable, and has at most one output y. And this is the most important part there within the definition, at most one. So it can either have none or it could have one. We cannot have x giving us multiple outputs for the same input. So, as you've seen in the past, a lot of times we refer to y as the dependent and x as the independent. So y being sort of the output of a function where x is our input. And so because y is kind of dependent on what x's value is, we call y the dependent and x the independent. If we took every possible value of x that would be allowed to be plugged into my function, which most of the time, only in certain types of functions do we have to put limits on that, but most of the time we're able to plug any value for x in, and then we'll get a set of outputs for those x inputs. So at any rate, the values that make up what I'm allowed to plug into my equation is called the domain of the function. The values that are going to be used as inputs or that can be used as inputs. And of course, with every input, we're going to get at most one output. And so those set of values, the set of y's, the outputs of my function, is called the range of the function. And when we designate a type of relationship as a function relationship, then one way that we symbolize that and show the user, whoever's interacting with that function, that this is not just a regular function, a regular relationship, a regular relation, but rather a function relation. Instead of the variable y, we will substitute for that this f parentheses x, which reads f of x. In other words, this is a function. It follows the rules of a function with the set of inputs of x. And so this is not f times x. A lot of times we'll look at that, f with the parentheses as meaning times, but this specifically just shows kind of this idea of like a machine where we're plugging in x's and then we get a result, which is our y. And so f of x, the symbol f of x, is used in lieu of a y. We'll just put f of x there. For example, most lines are functions. The vast majority. There's some exceptions here. But so if I had a linear equation and I wanted to show it as being a function relation, I could just write it as, instead of y equal to 2x plus 1, f of x equals 2x plus 1. And that shows the reader that this is not just a regular linear relationship, but a functional relation. We think of a function as kind of this like machine. And I think the best example is kind of your like keyboard, where you're going to type a letter, right? So you have your input X, and you have the expectation of an output coming out of this terrible looking machine that I've created here, which is your y. And every input should have a consistent output, right? So, for example, on a keyboard, we wouldn't hit the space bar and sometimes get a space and then sometimes get some other output, like an X. We're not gonna hit the space bar and get X as an output half the time and then have a space put in the other half of the time. So every X should have a consistent and reliable Y output. If we get more than one Y output, then it is not a functional relationship. And that's what we mean by every X has at most one Y. Now, that doesn't mean every X is only paired out with one Y. The way I said that is true. It is paired that way. But we can actually have two X's, so X1 and X2, so two different X's that will sometimes also give us the same Y output. So we can have two X's that give us the same Y, but we can't have a single X giving us this two different Y's. So we're going to look at some of those examples here. All right. So there's lots of different ways that we can sort of designate, besides writing out an equation, but we can designate kind of a function relationship. One is with ordered pairs, right? Ordered pairs can define a relationship of inputs and outputs. Our X's are my inputs, our Y's are my outputs. Another way to picture these is to look at it from a input going to outputs over here. And remember, our inputs, we describe those as our domain, our set of all inputs, and our set of all outputs is called my range. All right, so in our first set of ordered pairs, we have a collection, a set. We use this notation here and here, which denotes a collection, a set of inputs and outputs. It's sometimes looking at it in this format where it can be difficult for us to kind of discern things. But remember, if something is a function, every X should have at most one Y. So every input should have at most one output. So if we look at this, we have -1 going to 2. So we denote that here with this, -1 going to 2. And then later over here, we have a -1 going to -3. And then we have 1 going to 3, and we have 5 going to 2. In this particular case, if the question is, does this define a function relationship, we would say no. And the biggest reason, or the only reason here, is we have this -1 going to 2, and then that same input, -1 going to -3. In this relationship, we also had two inputs that gave us 2 as an output, right? -1 gave us 2, and 5 gave us 2. That by itself would be okay. Again, we can have different inputs giving us the same output. And one of the other illustrations beside the keyboard I would give you there is if we think of my inputs as cities and my outputs as population, we can have two different cities that go to the same population size, but we can't have one city having two population values, right? So this is the part here where we run into trouble, and that right there tells us that this is not a function relationship. All right, so the next question is the second one a function relationship? So one way to evaluate that is to just draw out your inputs and outputs and see what kind of relation we have. So we had -2 going to 1, and then we had 0 going to 2, then we had 2 going to 1, and then we had -1 going to -3. So question is this a function relationship? The main part where we would question that is when we have the 2 going to positive 1 and negative 2 going to positive 1. But remember, that's like 2 different cities tracking to the same population. That makes real world sense. And that's one thing about functions, is that typically they make real applicable sense in kind of a real world setting. And so that's okay. We can have different cities tracking to the same population output. But, and so yes, this is a function relationship. We don't have one input giving us multiple outputs. All right, when we look at a equation and we want to determine whether an equation defines a function, one of the things that we can do, this is a little more difficult, but one way to go about doing this is to look at and solve the equation for y. Because remember, the main idea here is that every x is only going to give us one y output. So if I look at the first one, and I had actually typed this in wrong, so I put an x there instead of a y. To solve this for y, we would want to get the y by itself. So we'd start off by subtracting 6x squared. Of course, we can't combine those two because they're not like, but that gives me negative y is equal to 12 minus 6x squared. And then to completely solve this for y, I want to get rid of that negative because we want just a positive 1y. And so we're going to multiply both sides by negative 1, which this would distribute to both of those. So that's negative 12, it was positive, and then plus 6x squared. So my y is going to be equal to, for whatever reason, I like to have the variables written first, but you can leave it this way, or you can write it as 6x. Whoops, again, there's those lines that pop up. 6x squared minus 12. Now, you may not be familiar, with this particular type of equation where we have x being squared, but any value I put in there is basically going to give me one output y. I'm not going to end up with multiple outputs for I'm not going to end up with multiple y outputs for the same x input. Now, I can show you, let's take positive 1 and negative 1. If I put in positive 1, I end up with 1 squared is 1, 1 times 6 is 6, and then 6 minus 12 is negative 6. Okay, well, that's one output for my input of 1. And if I put in negative 1, well, guess what? That's negative 1 squared. It's still, when we square a negative, it becomes positive, so we still end up with the same output. So 1 gave me negative 6, and negative 1 gave me negative 6. But again, we can have different cities with the same population. We can have different inputs that give us the same output. What we don't want to have is 1 giving us 2 outputs or negative 1 giving us 2 outputs. So this is just one number that I plugged in there, but it does show you, I wanted to show how, yes, the square does have an effect here because it allows us many times to have multiple inputs with the same output. That's kind of the effect of having that square there. However, that's not a problem in a function relationship. Now, taking a look at this function here, again, solving it for y, I would want to add x squared to both sides. So that would give me, that cancels out there, and I have 4 plus x squared here. And then I would need to take the square root of both sides to get y by itself completely and not have a y squared. Now, whenever we take the square root of both sides in an equation, we always have to take both the positive and the negative of that square root. So the result more than just the square root of 4 plus x squared. It's the positive and negative square root of 4 plus x squared. So for any input x, again, let's just use 1 because 1 is nice and easy. Y would equal the square root of 4 plus 1 squared. Well, 1 squared is 1, so that gives me the positive and negative square root of 4 plus 1, which is 5. And so my one input of 1 gave me both positive square root of 5, but 1 also gave me the negative square root of 5. And so we have one input giving me two different outputs. That makes it not a function relationship. So because of that y being squared there, that is a problem, and is a problem generally when we're looking at equations that are functions. So that's one thing you want to look for, is when we get y by itself, we end up having to take the square root of both sides, which leaves us both a positive and negative output. Okay, so we want to expand a little bit about the notation that we use in functions with that whole f of x thing. We don't have to use f a lot of times to designate a different relationship. We can use g or h or any really letter there, as long as we're just showing that this represents some sort of relationship, that is a function relationship. That x being there, we can actually specify certain inputs, and then you can be asked to find the output. So, for example, when we're asked to find the g of 3, that means 3 is my input. And so I can find that simply by rewriting my function here. It's x squared, so parentheses squared minus 6, parentheses plus 8. It's good to write those out. And then we've specified our input here in the notation, g of 3. And so 3 is my input. And now I want to simplify this using the order of operations, where we do operations within parentheses first. Well, we can't, inside the parentheses, it's just a 3. We can't simplify that anymore. So then we go to exponents. So 3 squared is 9. Exponents are powers. Then we do any multiplications. 6 times 3 is 18. And then we do addition and subtractions from left to right. So 9 minus 18 is negative 9, and then plus 8 gives me negative 1. So the g of 3 equals negative 1. There's kind of my function machine here. We have our input of 3, and then 3 gave me my output of negative 1. Let's go ahead and do this one, g of negative 2. Oops, let me switch. I'm going to switch my colors here, just because it contrasts it a little bit more. G of negative 2. And so we're going to rewrite that again, x squared minus 6 times x plus 8. And our input there is negative 2. So we do our squaring first here. So negative 2 squared is 4. 4. And then we're subtracting 6 times a negative. So that becomes a subtraction. Well, it's negative 6 times negative 2, which is positive 12. Right? We can think of this as a negative 6, and that is a negative 2. And negative times negative is positive, and then we have plus 8 as well. So that's a bunch of addition. 4 plus 12 is 16, and then 16 plus 8 is 24. So the g of negative 2 is 24. Again, my input of negative 2 gave me my output of 24. Fun, fun, fun. Let's do one more here. Well, on this page. We're going to do the other two as well, but I'm going to run out of room, so at any rate, we're going to have our input, and then we're going to write this out. So minus 6 times x plus 8. I'm almost running out of room here. So I'm going to redo that. But our input in this case is a fraction, 1/2, which everybody loves fractions, don't we? Yes. Okay, so 1/2 squared, that's, when you have a fraction squared, you can square the top and square the bottom. Kind of works out fine. So that would be 1 squared, which is still 1, but then 2 squared is 4. 1/2 times 1/2, 1/2 times itself is 1/4. And then we're going to subtract 6 times 1/2. Well, half of 6, right? Of is that word that means multiplication all the time. Half of -6 is -3. So we have a subtraction of 3. It's a positive 1/2 times a -6, so that stays negative there. And then we're going to add 8. All right, and then just doing this a little bit at a time. A fourth minus 3, let me go up here. If we wanted to rewrite 3, so it has the same denominator, this would be, we would multiply this by 4, which we have to do the same on top. So that would be 1/4 minus 12 over 4. That gives me negative 11 over 4. And so this is negative 11 over 4. We'll leave it like that in improper form and add 8 to it. So we got to do a similar thing here. I've got negative 11 fourths adding 8. Well, to get a common denominator again, I got to multiply the top and the bottom by 4. A lot of your calculators will do this work for you. But 8 times 4 is 32 over 4. Negative 11 plus 32. Well, that's like subtracting 11 from that. So that's 21, positive 21 over 4. So the result is 21 fourths. You could also express that as a mixed number. 4 goes into 21 5 times with 1 left over out of 4. So the g of 1/2 is 5 1/4. All right, the two that we haven't done yet is d here. So this is a little bit different. We have an a plus 2 as our input. So we have an expression that we're inputting into this function. Well, just like before, let's rewrite this, leaving out the x, putting parentheses in its place. I'm going to make it a little wider because I know I'm putting an expression in there. But then we're inputting a plus 2 and a plus 2. So now we need to do some algebra here in expanding this a plus 2 out. So a plus 2, I'm going to do this up here, times itself, a plus 2. That's a times a, or a squared, and then a times 2, which is, they're both positive, so 2a. Then we have another 2a, and then we have 2 times 2, which is 4. These two combine together to give me 4a. So that's a squared plus 4a plus 4. And so I've expanded that out. Now we're going to think of this as negative 6 that I'm distributing there. So negative 6 times positive a is negative 6a, and negative 6 times positive 2 is minus 12. So I've distributed and carried out the multiplication there. And then we have our plus 8. So now it's just a matter of trying to get rid of this. Okay, now I have to rewrite plus 8 here. Those lines that just kind of appear there. We want to combine any like terms. Well, there's no other a squared term, so that just stays the same. Then I have 4a and I have minus 6a. Those are all like terms that involve a. So 4 minus 6 is negative 2a. And then we have 4, negative 12. Positive 4 and negative 12 give me negative 8. And then negative 8 plus positive 8 is 0. And so that leaves me with 0 constant numbers by themselves. So this, in fact, is my output of a plus 2. And then we have another one. We have h there instead of the 2. So how would that affect this? So let's write this out. Okay, I can already see I'm going to run out of space. So let's try that again. So g of x plus h. So parentheses squared minus 6 parentheses plus 8. And here's our input of x plus h. And let's go ahead and up here again, I'm going to take out the x plus h times itself, where we have x times x, so x squared, x times h, so xh, and then h times x, so another xh, and then h times h, or h squared. So this is a binomial squared, x squared plus 2xh plus h squared. So this would be my first parentheses expanded there, x squared plus 2xh plus h squared. And then we're going to distribute this minus 6 to both parts, so minus 6x minus 6h, and then we have plus 8. All right, now we want to look for like terms that we can combine together. And what we're going to find is we don't have a lot of like terms here, do we? In fact, x squared plus 2, there's no other x squareds. There's no other terms that have x and h being multiplied, so there's no xh terms. There's no other h squared terms. In fact, these are all unique terms. And so none of them can be combined together. And so what I have here is the most simplified version of that. All right, we want to talk about the domain a little bit of our functions. We said at the beginning that most of the time with most functions, domain reaches, when we talk about domain, it's what are we allowed to plug into our equation. And with most equations, we can plug in anything we darn well want to plug into them, right? There's really no restrictions. The problems that we run into, we're going to look at with certain types of functions where we can't just plug in everything because we'll run into problems with certain inputs. But this sort of idea of domain is, and this is, we're just expressing this as agreement on domain. If the domain of a function that is defined by an equation is not specified, then we agree that the domain is the largest set of real numbers that results in real numbers as outputs. This is kind of the key thing. So we're going to say our default domain is all real numbers. In other words, we can plug anything into our equation most of the time. And so if we're asked to define the equation, that's kind of our default, all real numbers. Now, there's two different areas. Well, there's two main areas when we're dealing with equations where we can run into problems. One of the things we want to avoid is zeros in denominators. Whenever we have zeros in denominators, we say this is undefined. There is no real number, in other words, output when we try to divide something by 0. So we can never have zeros in denominators. So this is one thing we want to look for, because that gives us something that's undefined. So if it's possible for an input of x to result in the zero of a denominator in a fraction, then we've got a problem. We have to eliminate that possibility from our domain. We have to limit our domain such that that's not going to be a problem. The other thing that we don't want to have is square roots where we have some number under there where a is less than 0. We can't have negatives under square roots, or that's, most of the time we're dealing with square roots, but really it's any even roots, right? Where it's a square root or a fourth root or a sixth root. A cube root can have negative outputs, but so that's not a problem. It's looking for those even index. So actually, let me actually state this in a different way, because I'm saying a less than 0. A actually has to be greater than or equal to. So rather than stating it in a negative way, I'm going to state it in a positive way. It must be greater than or equal to 0. The square root of 0 is 0, so that's never a problem, but anything less than 0 is a problem. We cannot have negatives under square roots or even roots. So where n, my index, is even. Okay, so another way to write all real numbers in interval notation, where we always have lower boundary first, comma, upper boundary, we can write the default domain of most functions goes from negative infinity to positive infinity. And then we can kind of specify if there's problems or numbers or things that we need to exclude from that domain. So we're going to look at some examples here and see if we can describe what would be the domain of these. The other thing I wanted to mention before we just get into this is that another limitation we can have on domain is just real-world constraints on things, right? So if a function is describing, altitude of something, it's very possible that negative numbers wouldn't make, any real-world sense. And so domain, a lot of times, if it's representing some sort of real-world application, will usually have some sort of limitations. So there are real-world sort of story problem examples where domain is also limited. All right, but from a pure equation standpoint, we want to look for ways that inputs could give us zeros in denominators, or negatives under square roots. So let's take a look at the first one here. We have f of x equaling 1 over 1 minus x squared. So what we don't want to have is for 1 minus x squared to equal 0. Remember, it can be negative, it can be positive, it just cannot equal 0. And so we have to ask, is there anything that I could put in for x that would give me 0? Well, let's go ahead and solve this for x. If I subtract 1 to both sides, that gets rid of it here. I have negative x squared is equal to 0 minus 1, negative 1. And then let's get rid of the negative to begin to solve this for x. So we multiply both sides by negative 1. So now I have positive x squared equals positive 1. And if we take the square root of both sides, we see that x is equal to positive and negative 1. Remember, whenever we take the square root of both sides, we have to take both the positive and the negative solution. So in this case, if I were to describe the domain, there are two numbers I don't want to have. So I could do it like this. So there's two ways we can show it as There's two numbers I want to leave out, basically -1 and +1. So I can go from, if I'm doing it in interval notation to describe my lower boundary, upper boundary, and there's just a couple of things that we want to leave out, we think about from left to right. I'm going to go from -infinity all the way up to -1, and then we're just going to exclude the -1. With interval notation, we use parentheses with the infinities always, and we use a parenthesis if we're excluding something. So this is going all the way up to -1, not including -1. And then again, starting up from -1 all the way up to +1. This is a little tricky. And then we're going to, but again, not including +1. So because of these parentheses, we're excluding those. If I want to include it, I use a bracket, and we'll probably see that in another example. And then I'm also starting back up from 1 to +infinity. So we always think left to right, left to right, left to right with interval notation, lower boundary, upper boundary. So we're going from -infinity to +infinity. The U just means in conjunction with, right? Think of that as unified with. So we're going from -infinity to +infinity, but we're stopping at -1. We're going all the way to +1 and then on to +infinity. Another way to write this is in set notation, where we say x such that x is a real number, but x cannot equal -1 or +1. So this is a lot easier when we're just excluding like one number. We use x, and then this up and down line reads such as, or such that, maybe that is a better word. And then we describe the values of x that are allowed. It's a real number, but it doesn't equal these two values. Okay, so that's our first one. We just have to exclude two numbers that make it not real. All right, let's go to B and take a look at B and see what we can come up with this. For B, we have g of x, and it's equaling the square root of x plus 1. Now, with square roots, we know that the one thing we want to avoid is negatives underneath the square root sign. So I want to make sure that x plus 1, the expression under the radical, is greater than or equal to 0. So here I can use inequalities here to help me figure out my domain. And with that, let's go ahead and solve it for x. Well, this is a pretty simple one to solve for x. If I subtract 1 on both sides, I end up with x greater than or equal to -1. So this is telling me the values of x such that I will get outputs that are either 0, we can take the square root of 0, that's not a problem, or something positive, more than 0. They have to be x greater than 1. So my domain here, if I'm putting it in interval notation, lower boundary, upper boundary, would be -1 and everything larger than -1, so up to +infinity. I'm not just leaving out -1. Actually, I'm sorry, I want to include -1. So here's where, instead of using a parenthesis, I would use a bracket, because -1 actually gives us 0, but 0 is okay. We don't mind zeros underneath the square root. So here we actually want to include -1 because of that equals part of x greater than or equal to -1. If it was just greater than, then we would use a parenthesis. That would exclude that -1. If we're putting it into set notation, we use the set symbols, and then such that, so then we describe x. The domain is x such that x is greater than or equal to -1. We can usually just put it as, it's a real number, or just describe what values x can take on, right? In set notation, we're using the variable x to describe the domain. Okay, let's go on to C now. For C, We're throwing a little bit of a curveball in that we have a square root, but that square root is also in a denominator, so it also can't be 0. It's a little bit different than what we had for g. It's a different expression. It's x minus 1. So how does this change? Well, I want x minus 1, the expression underneath the radical, to be greater than 0. And is it allowed to equal 0? Well, no, because in this case, I wouldn't want to put the equals. That's not allowed, because if it equals 0, I have a 0, the square root of 0 in a denominator, and the square root of 0 is 0, so that would give us an undefined expression there. In this case, to solve, we just have to add 1 to both sides, so we see x greater than 1 is my domain. Putting this into interval notation, we would say then that we're going from 1, not including 1, right, because it's not equal to 1. So going from 1, not including it, use a parenthesis all the way up to infinity. So that's interval notation. In set builder notation here, we would say just x such that x is greater than 1. You want to be familiar with both of these notations. A lot of times we tend to stick with interval notation, but I want you to be familiar also with set builder notation, x such that, and then give a description of your domain. All right, our last one there, d, we have p of x, and we've got, again, the square root of this big, long thing, x squared minus x minus 6. It's not in a denominator, so we don't mind it equaling 0, but we want to make sure that that expression, x squared minus x minus 6, is greater than or equal to 0. And so we want to look at what are the values of x that will make this 0 or something greater than 0. Okay, well, with a trinomial like this, one of the ways that we can solve this, besides using the quadratic equation, is to, or the quadratic function, is to use parentheses and factor it out. A lot of times it can be factored. With a negative here, that means my signs have to be different, because my two last things here are what give me that 6. And I also want their sum to be equal to negative 1. And so we look at negative 3 and positive 2. Those two added together give me negative 1x. Positive 2 and negative 3x give me negative 1x. And then the product of positive 2 and negative 3 is negative 6. So I see that for my solutions here, x plus 2 must be greater than or equal to 0, and x minus 3 have to be greater than or equal to 0. So the 2 points, x, here we would subtract 2 on both sides, so we see x has to be greater than or equal to negative 2. And here has to be greater than or equal to 3. All right, so when you think about these, in terms of this type of equation, the x squared minus x minus 6, we know that this gives us a parabolic graph when we have it set equal to y. In other words, it's a parabola. If you remember, parabolas kind of do this. And in this case, what we found with these zeros, where we had it set equal to 0 for y, so whenever x results in a 0, that means we have a y-intercept in those places. What we found here is 2 places along the x-axis, and I'm just going to mark them out here, negative 2 and 3, right? Positive 3 and negative 2, where the function could dip below the x-axis. Now, sometimes certain parabolas will be upside down ones. So It could be that they dip below over here, on the after the 3 and before the -2. And then they're positive here. But think of it, if this is where y is equal to 0, I have my positive area up here and I have my negative area below. So positive above, negative below. So what we can do whenever we run into the situation, if we're not sure where y is going to be positive, is to pick some numbers between these. And I'm just going to randomly pick a couple here. I know that -3 is less than -2. I know that 0 is between -2 and 3, and I always like to put 0 if we can, and then 4. We're going to pick 3 numbers and plug them into this function to see what kind of result that we get. So let me erase this over here for right now, so we have some room. What we're after, remember, is something that's positive, an input that gives me a positive output. So let's start off with -3. So P of -3 would give me, and I'm going to write it without the square root. We're just looking for positive outcomes. So x squared minus x minus 6. Oops. Don't want to put x there. We actually want to put parentheses. And then put my input, which in this case was -3. So that's -3 squared, which is 9. Subtracting -3, so plus 3. Subtract negative is same as adding positive. And then minus 6. So 9 plus 3 is 12. 12 minus 6 is 6. So that's a positive outcome. That would be a positive outcome underneath the square root, and that's okay. That's allowed. What we don't want is negatives. So this works out. This area is allowed. Let's try 0 now. So I'm just going to change my inputs. Make this a little bit bigger so I can just erase the inputs. So P of this equals that squared minus 6, or I'm sorry, not 6, just minus x. Going back to our other one. And then minus 6. Our input now is 0. I love zeros because they just always work out so nicely because they pretty much just eliminate themselves. 0 squared is 0, minus 0, and then minus 6. So we have basically -6 as my output. That's negative. We can't have -6 under there, so that's bad. So we know that between -2 and 3, remember I just picked a random number somewhere between -2 and 3, and I got something negative. Not allowed. So I can't have the area in between those two. Let's try 4, and I kind of suspect, as I'm sure you do, that we're going to get something that's okay here. And let's see if that actually works out. It's okay, but we want to, we can have our suspicions. We just want to be able to confirm those. 4 squared is 16 minus 4 minus 6. Well, 16 minus 4 is 12, and 12 minus 6 is 6. We keep on getting 6. That's interesting. So at any rate, the numbers I randomly picked, and it was pretty random. I didn't know what the outcomes would be ahead of time. I keep on getting 6, is positive. And so this area up here also works. So the one area that I don't want to have as part of my domain is the area between -2 and 3. Remember, 0's okay, right? We can have equal to 0. So for my domain here, putting it into interval notation, I would go, well, we can go from -infinity all the way up to -2, including -2. So -infinity, parenthesis with infinity always, all the way up to -2, including -2. -2 would give us 0, which is okay. It's not in a denominator. And then we're going to combine that with, so we put a little u for united with, the set going from 3 to all the way to positive infinity. That's how we would put this into interval notation. As far as there's a couple ways we can express it with set notation, x, such that we can say x is real. But let's see, actually just using two x is real and x is less than or equal to -2 in union with x being greater than or equal to 3. Close that off with the set notation, and that would describe it in set notation. When we talk about finding the range, we've talked about the domain. And the domain we've defined as numbers we're kind of allowed to plug into a function, basically allowed to the point where they don't give us something that's undefined, like negatives under square roots or zeros in denominators of fractions. Pretty much most domains are all real numbers, but then we get certain types of functions where we have to limit the domain. The other times where we might limit the domain is within applications. So there's real-world restrictions on a particular function. And so we have to limit the domain to make it fit within certain criteria or what have you. So many times a function will just be limited in its domain for some reason that usually goes back to context. So there's some reason why we're limiting it. Here, when you look at the function f of x equal to x squared, there's no way that I'm going to get, with that actual function, any zeros in a denominator or negatives under a square root. So that equation would naturally would have a domain of all real numbers. There's no restrictions on it. So we would say negative infinity to positive infinity. But in this case, this would be typically my domain here. But in this case, we've limited the domain. And we've said it only goes from 3 to 5. Those are the numbers we're allowed to plug in, including both of those numbers. So for some reason, which we don't really have a reason here, we've got a limited domain. When we talk about range then, it's a little harder for us to just pick out the range because the y, the output, is really dependent on what the input is, and then it's also dependent on what the relationship is, right? What is the equation that we're dealing with? With y equal to x squared, we tend to get like a parabola, right? So there isn't just all real numbers. There's some point on y, wherever this is, there's some y that's like the lowest value of this particular thing. So with range, since range is dependent on the input and the type of equation that we have, it's a little bit harder for us to find that sometimes unless we have a graph. But here they're just kind of asking us to do an exercise. They ask, is 10 within the range of f, given that my domain's been limited from 3 to 5? So let's look at that. If I have the low point here of my domain starting at 3, right, 3 is going to be the smallest number we're allowed to plug in. And we know that the function is x squared, so we'll put 3 squared. We know that the output is 9. That's really close to 10. So if we look at what the result of 5 is, that would be 5 squared, which is 25. We can see that we have kind of a rising set of numbers there. And so my outputs are going from 9 to 25. 10 then would definitely be in the range, right? It's something slightly above 3 as my input, because f of 4, in between 3 and 5 there would give me 16. So I know that 10 is going to be an output. It's not asking me for what the x input would be to get 10 as an output. It's just asking is 10 in the range. So that's kind of a yes and no question. We would say yes, 10 is within the range of f. All right, this next question asks, is 4 within that range of f? Well, we can kind of figure that out pretty darn quickly here, because we knew that 3 gave us a result of 9 and 5 gave me a result of 25. 4 is less than my output for my lowest domain value of 3. So we can see that 4 would not be in the range. In fact, 2 squared would give us 4, right? And 2 is not in the domain. It's starting at 3. So this is a hard no there. Okay, well, it says now find the range. Well, we saw that range went from 9, including 9, right? Because we included 3, went all the way up to 25, and then included 25 because 5 was included as part of the domain of f. So my range in interval notation would go from 9 to 25. We could also put it in set builder notation. Where we say set builder not y such that, and then I put 2 less than symbols around y. And then I want to put the lower boundary here, the upper boundary here. This is a trilinear inequality. We use 2 less than symbols, and we put the lower boundary, upper boundary, because this could be read from left to right as 9 is less than or equal to y, which is less than or equal to 25. Meaning-wise, we would, to put it in terms of y, because y is what we're trying to describe, I could start out by saying y is greater than 9, because I'm reading it backwards, right? I'm putting it in terms of a relation to y. In other words, if 9 is less than or equal to y, then y is greater than or equal to 9. I'm reading it backwards, and so we can actually use the opposite word there, or concept, greater than. So y is greater than or equal to 9, and at the same time is less than or equal to 25. So I'm giving that in set builder notation. This time we're doing it in terms of y because we're doing it for range, and range is an output. It's part of it's the y rather than the x. When we have a graph of a function, we looked at previously, like, how can we tell if something actually is a function or is not a function? And when we actually have the graph, that can help us figure out what the range is. It can help us find out what the domain is. But it can also help us determine whether it's actually a function or not. It's a nice, easy visual test. It's called the vertical line test. Basically, if a vertical line drawn anywhere within your function intersects in more than one place, then that particular graph is not the graph of a function. If it only crosses in one place for every possible vertical line you could draw, then it is a function. You can see here with the ordered pairs, we have the same input a, which that's my x value, and in fact, x equal to a, as we see here, describes a vertical line. Vertical line is always described by x equal to some value. At any rate, x equal to a produces 2 outputs, b and c. So my input of a goes to 2 different outputs, b and c. That's like one city having 2 different populations, or one hitting the space bar and getting a space sometimes and then getting maybe an x another time, so it's not consistent. That does not represent a functional relationship, so we would say it's not a function. Again, a function is just a set of inputs and outputs, so we've seen how ordered pairs can be a function as long as every input has exactly one output. Here, my input for x at this point has 2 different outputs, that y and this y, whatever those values would be. Maybe it's a 1 and a 3, right? So the same x giving me two outputs, y, and so that is not a function relationship. All the other points, a vertical line would only pass through one point, but here it passes through two, and so that eliminates this set of ordered pairs being a function relationship. Again, we can see with the y-axis, it's passing through 3 points. That's a vertical line. Here's another one. More than 1 point, not a function. Here we can draw lots of vertical lines, and at every point, they're only passing through a single point. And so forget that diagonal one. That's the computer doing weird things. I can try to erase that, but it starts erasing the graph. Anyway, this particular one, yes, it's a function. Do a little celebration there, dance. Again, vertical line passing through a single point every time. So yes, this is a function. Every input is giving me exactly one output. So a vertical line test, if we have the graph, is a great way for us to discern whether or not we have a function relationship. Okay, so for this one, it's going to ask us to do some stuff with this function. So cool, we're given that it's a function, right? What they want us to do is to do some stuff with it. The first thing is, let's see if one input of 1, output of -3 is a point or is a solution for this function, is an input-output result. So we want to substitute 1 in there. 1 squared minus 2 times 1 minus 3. Well, 1 squared is 1, so that's 1. 2 times 1 is 2, so 1 minus 2 minus 3 going left to right. 1 minus 2 is -1, and -1 minus 3 or plus -3 is actually -4. So 1 actually gives us an output of -4, not -3. So the 1, -3, not a solution, does not satisfy the function or the equation. The second part says find all values of x such that x5 is on the graph of f. In other words, what value or values for x gives me 5 as a result? Okay, well, that's a great question. Remember that 5 is my output, right? And y is always the output, and f of x is a substitute symbol that we use for y. So if I want to know the output of 5, what inputs give me that output, I have to swap out. I'm not finding the f of 5. I'm swapping out that whole result. F of x represents the output y, and my output y is 5. So in this case, I'm not finding the f of 5. That would be 5 as an input, 5 as an x. We want f of x to result in 5, and we want to figure out what inputs give me that. For a quadratic equation like this, we always have to set it equal to 0. And then what we're hoping to do, -3 minus 5 is -8. What we're hoping to do is to hopefully be able to factor, because that's the quickest way to do this. And when we factor, we're trying to write this statement of addition and subtraction of 3 terms. We want to turn that into what it would be as a statement of multiplication. Why? Big reason is because we have a 0 over here. This goes back to the rule of 0 as a product. If 2 numbers are multiplying to give me 0, the only way that can happen is if A is equal to 0, not A is equal to 0, or B is equal to 0, right? If it was 0 times 2 or 2 times 0, if one of those numbers is 0, then the product or the resulting product will be 0. But this is really the only way it happens in multiplication. So at any rate, that's the idea as to why we want to turn this into multiplication. I want to simplify this down so that I can solve these individual parentheses with 0. And anyway, we'll get to that here in a second. So with a negative product, these two numbers that we find here need to multiply to give me 8. So with 8, we have a couple of possibilities. It's either 2 times 4 or 1 times 8. With a negative 8, which is what we have, the symbols have to be different. That's the only way we get this times that, giving me 8. So it's got to be plus or minus. And since they're going to have opposite signs, I also want their sums, the inners and the outers, to add up to negative 2. So with different signs, they need to have a difference of 2. And 2 and 4 do. So I'd want to put 4 here, 2 here. We see that 2x and negative 4x results in negative 2x, which is what I wanted here in the center. I have to go back and redo this. The only other way that you can find these solutions is by using the quadratic formula, identifying a, b, and c, and you know that is negative b plus and minus square root b squared minus 4ac all over 2a. So that's the other way you can do it. If you can factor it, it's usually a little bit easier. Okay. So with these with this as my factored version of that trinomial, now what I want to try to do is to figure out, all right, what value for x would make this parenthesis equal to 0, and what value for x would make that parenthesis equal to 0. Well, this is a pretty simple one. We can look at the first one and see, oh, okay, if I substitute a negative 2 in there, negative 2 plus 2 is 0. So negative 2 is one of my solutions. And here I can see that positive 4 minus 4 would give me 0. So 4 is my solution there. You could also just take the whole statement, set it equal to 0, and solve for x. Right? So x equal to negative 2 is one of the solutions. If I set the second one equal to 0, we add 4 to both sides, we see x equals 4. So that's another way to just get that. Especially if these are more complicated, if there's a number in front of x as well, it's a little harder to just get the solutions right away. But these two solutions, negative 2 gives me 5, and positive 4 also results in 5. So, is that a function then? Well, yeah, it is. Because we can have different cities, right? The different inputs. So you type a city into your keyboard. Two different cities can have the same population. But we can't have, if this was backwards, if 5 was in the x spot, 5 as my input could not result in two different outputs. So, but that's not what they're asking. They just wanted to find out what are the solutions, what are all the x's, so that I get 5 as a result, and here are my solutions. Okay, on this next one here, it asks us to find all the y-intercepts for the function. So remember that when we want to find a y-intercept, 0 goes into the other variable. So 0 for x always gives me b. Well, I'm using b there. You could use any letter, but b tends to be what we use sometimes as our y-intercept. So this represents 0 as my input. All right, we're inputting and resulting in my y-intercept. So in other words, I want to find the f of 0. So that's 0 squared minus 2 times 0. Isn't this great? Super easy. 0 squared is 0. 2 times 0 is 0. So we're just left with negative 3. So my y-intercept is 0, negative 3. Now x-intercept's not quite as easy, but remember that to find the x-intercepts, we put a 0 in for the y. Y is f of x. So instead of f of x, I'm going to put 0. And now I have to find the x values. Again, if it's set equal to 0, we can factor it and hopefully get to a result that we like. I know it has to be positive and negative because, just like the previous one, I'm going to get negative 3 as a product. The only way we get negative 3 is with a positive and a negative number being multiplied. I want a difference of 2, or I want the sum of my inners and outers to get me negative 2. So I have to look at the factors of 3. Well, there's luckily only one set of numbers that multiply to give me 3, and either a negative 1, positive 3, or a positive 1, negative 3. But in any rate, I want their addition, their sum, to be negative 2. So that means I want to have more negatives than positives. So we put the 3 with the negative. My inners and outers, this is 1x, outers negative 3x. Adding those, we get negative 2x. So I know that this is, and so my solutions for x are negative 1 and positive 3. Those are the values that if I plug those in, I would get 0 within those smaller parentheses, and then 0 times the other parenthesis would result in 0, which is my product here. So the x-intercepts are negative 1, 0, and 3, 0. Again, that's okay. 2 different cities, same population, 2 different inputs, same output. That's allowed in a function. And so we're good right there. So for the next one, this is our last kind of idea here. And we're going to look at what the average rate of a function, rate of change for a function would be. This is something that when you get to calculus becomes a very fundamental idea that we use in calculus. But it all just goes back to slope. If you remember, when we talked about slope, slope is the average rate of change, right? And we're used to looking at slope when it comes to a straight line. But many graphs are not lines. So I'm just going to draw kind of a sample here of a graph that is not a line. Let's say we have something like this. And I'm going to put A here and B here. And I'm totally just doing this for a visual. Actually, let's put B out a little bit further here. It can be anywhere. I just want a good example here for us to look at. So B, is this point up here. And then we have this value A here. So if we're going from A to B, so we're at A, we're kind of tracking along, and we stop at B. Let's say we're hiking, maybe. And we want to know what's the average change that I made along this hike. Well, what we're going to do is we're going to take these points. So A gave me the result of y when I plugged A in. Excuse me, that was a sneeze. When I plugged A into my function, I got a result. So we're going to write that as f of A. That's my y, right? The f of A would represent the result when I plugged A into the function, whatever it is. The graph is representing the function here. So this would be that point there. And then B, when I inputted it, I got some result. And so we'll put f of b as my y result of that. And so what we're doing when we find this average rate of change is we're actually saying if I drew a line through these points, what would be the slope of that line? Okay? Sounds very, complicated and like, what? All these symbols. Well, that's all we're saying here. Notice that f of b, this would be like my y2. F of a, this is my result of plugging a in, so that would be like my y1. And then we have my x2 and my x1, right? These are my inputs, b and a. And the one thing we're saying is b can equal a. Can you think about why that would be? Well, b can't equal a because that would give me a 0 in this denominator, and we know that's not allowed. Okay? So in this case, there's no specifics here. I'm trying to give you a visual to go with this idea that if a f of a and b f of b are 2 points on the graph of any function, the average rate of change as x goes from a to b is defined by this arc of f from a to b. So I want to basically find my change in y over change of x. All right, so it's that simple. It's the slope formula here. So let's put this into practice. So with a specific function now, that's our function here. They want us to find the average rate of change as x goes from 1 to 3. Now, we don't need a graph to do that. I just need to figure out what the y output is when x is equal to 1 and what the y output is when x is equal to 3. So I need to find the f of 1 and the f of 3. This will give me my y, right? X is 1, what's my y? X is 3, what's my y? Okay, so 2 minus 3 times 1 squared and 2 minus 3 times 3 squared. Okay, well 1 squared is 1. So that gives me 2 minus 3 times 1, or 2 minus 3, which is negative 1. So 1 gives me an output of negative 1. 1 is nice and easy. Now, evaluating this one, I would first do my square first. So 3 squared is 9. So now I have 2 minus 3 times 9. Well, 3 times 9 is 27, so that's 2 minus 9 times 3, 27. 2 minus 27 is negative 25. So 3 results in negative 25. There's a big dip there in our graph going from 1 to 3. We start out at negative 1, and then by the time we get to x equal to 3, we're at negative 25. So now, if we want to find the average rate of change, I want to find the change of y with relation to x changing. So here's my 2 points. We're going to go negative 25 minus negative 1. That's a tricky part here. Remember, sometimes it's better to, I'm going to put this in a different color here, to write in your subtractions on either side and then input your numbers. For the x, it's actually pretty easy, but especially when you've got negatives, this subtraction of minus 1 becomes plus 1, and that's really important to discern there. So that's negative 25 plus 1, which is negative 24. And on the bottom, we started with negative 25, so I have to start with 3 and then 1. So that's positive 2. So we see negative 12, 24 divided by 2, negative 24 divided by 2, negative 12 is my average rate of change. As x changes by 1, y changes by negative 12. Right? You could put every number over 1, right, when it's a whole number. We saw with our graph there that this is change of y over change of x. So negative 12, it went down every 12, every time 1, or x, changed by 1. That represents the end of this particular lecture. So hopefully this will give you a good start on our homework. So go ahead and do the homework problems that are associated with this. We're talking about functions, their graphs, their ordered pairs, discerning what's a function, what isn't a function. You could be given an equation, ordered pairs, things that are being mapped to one another. You also know if you have a graph how to determine whether it's a function, and also just practicing working with that notation. So writing those things out on paper, solving these equations, this is all stuff you want to be practicing. Make sure to bring any questions that you have to either our embedded tutoring class or to me during my office hour, what have you. I'm happy to help you with any of your questions, and then we'll see you next time we meet. Thank you.